Or not, exactly, ENS or not. So, which I guess, you know, you like sort of to have an egalitarian system in the state, so you like to imagine that, you know, Berkeley used to do this thing that I thought was great. So they would, Berkeley, I mean, some people hate it because they would admit huge numbers of grad students and then children. But, I mean, but you get a chance, right? So, you know, I like it. It's a shot, and then you know. Which makes it nice because we can actually prove something like, holy shit, that works. This is my peanut. This says, please feed him peanuts so he dies.
So before I start the actual part of the lecture, I want to make a couple of comments about things that can happen at a conference. Because as you go through your career as a mathematician, you'll attend many conferences. They're usually fun things. You meet a lot of people, go to different places, eat fun food. But here are two particular things that can happen. Sometimes you learn something useful. For example, in 1989, there was a conference at Washington University in St. Louis, and this guy named Bill Fulton gave 5 lectures on a book he was writing called Introduction to Toric Varieties. And that's a pretty good way to learn about toric varieties. And then 2 years later, a second good thing happened. It's because sometimes somebody can ask you a good question. And so 2 years later, I was at a conference in Cortona in Italy, having a conversation with Bernd Sturmfels. I was talking about some research I was doing at the time. It involved certain surfaces in a weighted three-dimensional space. And when I took the defining equation, I could create an ideal of partial derivatives in the weighted polynomial ring. And the graded pieces of the quotient told me something about the cohomology of the hypersurface. And Bernd said, you should be able to do that in a toric variety. I said, yeah, but you need a ring. And so I went and thought about it. And a year later, I created mathematics I'm about to tell you about. And so these two things had a profound event. It led to books, it led to summer schools. It's literally the reason I am standing here in front of you today. So I recommend conferences. And it's hard to predict when the good things will happen, but they can. So let's actually do the mathematics now. So this is chapter 5. And basically the goals that we have is I want to generalize the quotient construction of projective space. But this construction not only gives you the variety, it gives you the coordinates, the homogeneous coordinates. So I want to generalize homogeneous coordinates. I also want to generalize what it means to homogenize a polynomial. Because the idea is that if I have just an affine polynomial, say of degree d, so this is just affine, how do I get a homogeneous polynomial? Because basically I have one more homogeneous coordinate, x naught. Well, what I do is I replace all the variables with xi over x naught. That'll of course introduce some denominators, but because it has degree d, I can clear them all by that. And so we're going to learn how to do all of these in the toric context. Now I'm going to start with the quotient construction. And in the quotient construction, the homogeneous coordinates will be sort of implicit, and then we'll make them sort of a bit more explicit, and then toward the end of the second hour, we'll learn about how to homogenize. So we're going to work with a toric variety. I'm going to make one assumption about the toric variety, which is that it has no torus factors. And remember that that means that the U sub rho, the ray generators, span n sub r. So basically we want to make sure we have enough rays to make this work. And then we have an exact sequence. Where we take our character lattice, and remember then we take the divisor of a character we have that map right there, and then the co-kernel is the class group. And then because the UI span NR, this map, which is built on these dot products, is injective. So we actually have a nice exact sequence. And the rough idea of the quotient construction is that X sigma is going to be isomorphic. Well, I need an affine space, because here I had an affine space. In the affine space, it's basically, because notice that this is the direct sum over the rays. And so it's basically the number of rays. And so I'm just going to simply write my affine space as C of sigma 1. So basically the coordinates are indexed by the rays. So there's our affine space. But then you have to remove some bad stuff. And it turns out the fan will tell you what to remove. And then you take a quotient. And of course here, when we first see this, we wrote it pretty naively. we now, because of last night, have a slightly more sophisticated notion of quotient. And so there's basically going to be some nice group, which I will describe in about a minute. And then this is actually going to be not a bad, it's going to be a pretty good quotient. Because remember, the most basic level of quotient was a good categorical quotient. The absolute nicest quotient was the geometric quotient. And in between, we had the almost geometric quotient. And that's what this is going to be. So in general, it's an almost geometric quotient. Or in some cases, and we'll be able to characterize that explicitly, it'll be just a geometric quotient. So that's the goal that we're aiming toward. So I basically have to tell you the group, I have to tell you the bad stuff, and then we have to prove a theorem. And so the idea about the group is we have this nice exact sequence. Let me call that star. So we simply apply this functor to that exact sequence, and we get a nice exact sequence of multiplicative groups. So we get Hom Z of the class group into C star. So basically this is a little algebraic group, and it's, because remember this is this is a finitely generated abelian group. It's got a free part that's finite. So it's got some finitely generated free part, and then there'll be sort of possibly a finite torsion group. And so this is not going to be a bad group. And it turns out that's what G is. And then one way to think about it is that basically this group is invented so that its character group is this guy right here. Then of course just working here, and of course notice that this is just basically Z to the sigma 1. And so I'll write it that way. And of course this is just C star. Am I standing too close, or? Yeah, so I have to. Not sure what the problem is with the reverberation. And so notice that this is the big torus of the affine space. So I have this really big torus, and then of course I get this. And then looking at the last part, I map into that. Does anybody remember what that is? Turns out that's our torus T sub n. So notice that we've already got something that makes pretty good sense, because I want to achieve my toric variety is this quotient by G. Well, sitting inside of this toric variety is its torus. Sitting inside of this, we will see that basically this bad stuff it's all disjoint from the big torus. So sitting inside here, you have the torus. And so in particular, the torus here is going to be the quotient of the torus here by G. And that's exactly what this sequence says. And I'm writing 1 here because we were thinking of these groups multiplicatively. Now you might worry that this is not an exact functor. So how does it take an exact sequence of something just plain old exact? And that works because this is a divisible group. So we actually get this nice little exact sequence. So that's part of stuff. And I'm going to actually come back to this, and I'm actually going to give you a formula for G, because right now it's a very abstracty thing. Then the next thing is the set and here's part of the interesting fact is that basically if this construction is going to recover the toric variety, then this construction somehow has to know the whole fan. And yet if you think about it, this only knows the rays. And also the group G, it turns out the group G is just determined entirely by the rays. So right now I'm completely ignoring all the other fans in the cone. And it turns out that that's where this set comes in. That this bad set gives the information that tells you what the cones are. So let me write that down. So you only need sigma 1 for G and the affine space. You need all of sigma for this guy. And it turns out that the bad stuff, of course, is going to be a variety, so I'm going to tell you what its ideal is. But then I need a ring. So basically, I want the coordinate ring of our affine space. And remember, the deal is that I have one variable for every ray. So I'm going to call the variables x sub rho. Question?
You said that we only need sigma 1 for G as well. But G depends on the class.
Right, but the class group depends only on sigma 1. Because of this exact sequence right here. See, this exact sequence only uses the rays. So that's one of the tricks of the trade. If you're trying to compute a class group, you can ignore all the other cones. All you need are the rays. Whereas here, so even though I wrote x sub sigma, that class group only depends on sigma 1. But now we have this polynomial ring, and then what I'm going to do is for each cone in the fan, I'm going to get a monomial. And I'm going to write the monomial as x sigma hat. And the hat means ignore the stuff from sigma. So what this is the product of the variables where rho is not contained, whereas rho is not an array of the cone sigma. So it's basically the product of all the other variables. And I will give you some, once we start seeing examples, we'll see that that's a very natural gadget. And then B of sigma is just the ideal generated by these. And notice that this is a monomial ideal, and in fact these are square-free monomials. This is a square-free monomial ideal. This is a really nice monomial ideal. And then Z sigma, the bad stuff, is simply the variety of this ideal. And one thing to note is that these are monomials, and so when I set this equal to 0, that's basically saying one of the coordinates has to be 0. So in fact, this is actually going to be a union of coordinate subspaces. And so in particular, that's why the bad stuff is basically disjoint from the big torus. And so that's why the torus of C sigma 1 lies in here. And it turns out that if you sort of think through what's going on, it turns out that a monomial ideal is determined uniquely by its minimal generators. And the way we've set things up is the minimal generators here are the x sigmas, for the sigmas the maximal cones. And so from this ideal, I can read off what the maximal cones are, and then I get all the other cones just by taking faces. So this ideal encodes the full information of the fan in this one ideal. This is, because lots of times people say, oh, a monomial ideal. It's generated by monomials. It's got to be easy. And the answer is no. Monomial ideals can be very complicated gadgets because you can encode a lot of combinatorial information into a monomial ideal. And this is a classic example of that. So that's the bad set. So what's the theorem? Is that, so the first part of the theorem, so again we have x sigma no torus factors. So it turns out that when I take this guy, remove the bad stuff, and mod out by the group, and notice that the group action is totally obvious, because G is a subset of the torus here, which clearly acts on the affine space. And then furthermore, this is, not only do I have an isomorphism, but this is an almost geometric quotient. And then the second part of the theorem is that, of course, the kind of quotient we really like is an actual geometric quotient. And so it turns out that this is a geometric quotient. If and only if the fan is simplicial. And so it's a very satisfying bunch of stuff. So what I want to do is I want to give some examples. I want to say a few words about the proof. But the thing is, if I'm going to give some examples, I need to say a little more about how you actually calculate this group G. So let's do that. And also, by the way, we want to make sure that G is the right kind of group so that we know that we have nice quotients. So let's describe G, and that's lemma 5.1.1. So of course, part A is really just the direct consequence of this, namely, what's the character group of G? And the answer is the character group of G is the class group of the toric variety. Now you might wonder, why do I say character group? All before I've been saying character lattice. We have M. M is the character lattice of the torus. Well, the answer is this might not be a torus, and so the theorem is that G is, when you take the connected, so the point is this might not be a connected algebraic group. When you take the connected component of the identity, what you get is a torus. And in fact, in this case, you can split it and you get a finite group. And the point is where the finite group arises because the class group might have torsion. And so this is reductive. And so all the nice theory I described last night applies. And then the third one is you can actually write down equations. Because, after all, I'm claiming this is an algebraic group, so I should be able to write down the equations in here that it satisfies. And so what I do is I pick a basis of M. And then what's G? Well, first I'm simply going to describe G as the kernel of this map. And so what is that? And so I take, so I use this notation, T sub rho. That means it's a bunch of points indexed by the rho sigma. So that's basically a point here in this torus. And then how does something here give an element here? Well, it gives a homomorphism from M to here, and what that homomorphism is so basically I have to somehow use this data to describe a homomorphism from M into C star, and the obvious way to do that is it's the map that takes M and maps it to that gadget right there. And again, remember that that's because this map, the map from M to this, was built by those inner products with the use of rows. And so that's what turns, so when I take something in here, this is the element I get, it maps M to C star. But I want to be in the kernel. So I want this map to just be basically I want everything to match the identity. So I'm looking for pairs where for every element of M, this is equal to 0. Well, that's infinitely many equations. But the point is it suffices for these equations to hold on a basis of M, which I'm calling E1 through En. So in fact, this is simply the T rows with the property that the product of the T row. So here, instead of picking all M, I'm just going to pick M to be that. So it'll be this to the EI, U row equals 1 for I goes from 1 to N. And so here's a finite system of equations. And again, because that's a point in here, I've got this little system of equations. The solutions are G. So that's what G is. Now we're ready to do an example. And not surprisingly, the first example is projective space. So how does all this structure give us projective space? So this basically combines examples 5.1.2, 5.1.7, and 5.1.12. So in one of these we work out G, and another we work out the exceptional set. in the final one we give an application of the theorem. So remember that we have U1 up to UN, and then we also have U naught, which is minus the sum of the others. So these are the, the ray generators. So in this case, we have, so notice there's n plus 1 rays in the fan for Pn. And so I have a variable for every ray. So we get our usual polynomial ring in n plus 1 variables. Now what's B? Well, remember the comment I made back here is if you want to find the minimal generators, it's sufficient to use the maximal cones of sigma. And the maximal cones here, well, how do I get a maximal cone of this fan? What do I do?
Choose n rays.
I choose n rays, or I omit 1. But suppose I've picked a sigma that omits 1. Well, so notice what happens if I omit 1, then this is all the rays. There's only 1 left, the one I've omitted. And so in fact, if I omit the first ray, or if I have a cone where I sort of just use these, that means, I basically want to ignore these ones, because again, I want to ignore the ones that come from there. So in fact, I just get x naught, x1 up to xn. And again, those are the minimal generators, and that says that I get 1 cone by omitting U naught. I get another cone by omitting U1. I get the final cone by omitting UN. So from this, I can read off the n-dimensional cones just from that ideal. And then, of course, what's Z of sigma? What's the variety of that ideal? It's just the origin. So the bad stuff in this case is just the origin. Now let's compute G, because we've got our general formula for G. And so what we have here is, again, I have a point in the torus, and so this is in C star to the n plus 1. It's in the torus of our big affine space. And then what I do is I get an equation, so I'm going to get n equations. I get an equation for E1, I get an equation for E2, I get an equation for En, and I get a whole bunch of stuff that's equal to 1. So what equation do I get for E1? Well, I have to take E1, and I have to basically zap it. So I'm just taking E1 and I'm zapping it with all the U rows. And so I'm zapping it with this one and all of those. And of course, when I zap it with this one, so I'm going to get T naught. So T naught is going to appear because when I zap, because that corresponds to hitting U naught with E1, what exponent do I get? I just get -1, that minus right there. And then also, T1 is going to appear because T1, that corresponds to U1. And when I hit that with, and this is the dual basis, I just get exponent 1. And then what am I going to get when I use E2? I'll still get T naught, because you see everybody appears in T naught. And so when I hit T naught with E2, what do I get for the exponent? -1. And then who else am I going to get? I'll just get T2. And that continues along all the way. So I get T naught inverse Tn. But what do these equations tell me about all the Ti's? They're equal, because this is equal to 1. So that says that T naught equals T1, T naught equals T2. So in fact, G is on the nose. So there's, here's a group that's isomorphic to C star, and this tells us how C star acts. It's just the usual action of T star. And so by the theorem, I get that Pn is indeed Cn plus 1, the affine space coming from the rays, modulo the bad stuff, which is dictated by the maximal cones, modded out by the group. And so there's the quotient construction. And furthermore, notice what kind of quotient is this? Because remember, there's two kinds of quotients we're dealing with. And it's a geometric quotient because, in fact, this is a smooth variety. And remember, every smooth variety is simplicial, so it's guaranteed to be a geometric quotient. So that's really nice. Let's do another example. Let's do a weighted projective space. Now here we're going to have to work a little harder. It's going to have a lot in common with this one. The big exception is the group's going to be different. So remember, this is example 5.1.4 for weighted projective space with our usual hypotheses. Remember, n is z to the n plus 1 modulo the subgroup generated by the vector of weights. Ui is the image of EI, and the relation between the UIs is, instead of this, in projective space, the UIs sum to 0. Here, it's the weighted sum is 0. And then the idea is that, the fan the fan is actually the same kind of game, is that you basically, where the maximal cones are basically, omit, the maximal cones are generated by all but one UI. So I just decide who to omit. And what that tells me is that the ideal I get is the same one as here. And so that implies that B of sigma is the same thing. So you see I have the same affine space, Cn plus 1, and I have the same bad stuff. So again, the whole place the difference comes from is I'm simply using a different group action. And then for G, I look at the exact sequence that gives the class group, and the point is that the standard basis vector here maps to Qi here, and basically M is just the kernel of this map. In fact, if you take this presentation and dualize it to try to get the dual lattice, you actually get exactly this description. And so then what I'm going to need to do is, I want somebody here that maps to 1. And remember, we can do that is because my QIs are relatively prime, so I can find QI such that summation BI QI is equal to 1. And so the vector of B's here maps to 1 here. And that's going to be important. And now let's take a point contained in G. Now when I did it here, I took a point in G and my equations are all nice little simple harmless things, and I discovered all the T's were equal. And so in fact, notice that this T could be T0, could be T1. So if I'm given this, to get just the T, I could just take any of them. Here, these are all going to involve a single T, but it's not going to be just one of them. It's a more complicated gadget. Turns out the T we want is going to be the product of the TI to the BI. So it's these BIs right here that do it. So this is a slightly tricky argument. What? Yes, I do. Thank you. I could start at 1, but it'd be wrong. So, yeah. Now, the other thing, here I just said in a very cavalier way, take a basis of M. And it's true that M has a basis, but I can't write down a nice basis of M. So I can't quite replicate what I did there so easily, but rather than writing down a basis, I at least can write down some elements of M. So here's an element of M, is that, so let's fix I. Because what I'm trying to do is I'm going to try to figure out what T sub I is. And then the thing to note is that Q sub j, E sub I. So now the E sub i's are the basis vectors here. So this E sub I is that E sub I. I want a minus there. And then I want plus Q sub I, E sub j. So if I look at this little guy, that's in here. And notice that because EI and EJ map to the appropriate Q's, this is actually in M. So the point is that I can't find the basis of the kernel, but I can find some pretty nice elements of the kernel. And so in fact, let's for the time being, let's just fix I and J. So I can find a whole bunch of elements in the kernel. And so what that tells me is that, and remember the equations that I have this equation for any element of M. I apply it here, and when you work through what stuff is you get so in fact I get, it turns out because only two things appear here, I'm simply going to get Ti, and I'll get Ti to the minus Qj because of the EI there. And then here I will get Tj to the Qi equals 1. And so what we discover is that one of these, so the ith, because remember this is just an element of G, and I take the ith thing in this element of G and raise it to the power Qj, that means I can switch the indices. This is Tj to the Qi. And now I'm in pretty good shape. Because remember we have this T that I defined. So let's take this T and let's raise it to the Q I power. So what's t to the qi? Well, I'll just use the definition. Starting at 0. And so I get ti. So I take this and I raise it to the qi. So I can do that, and that's, so that's tj. Yeah, so in fact, let me put a j here. Yeah, so let's think of that. So it's the product is j goes from 0 to n. And so that's what that is. And then when I raise it to qi power, I can put the I exponent in here. And of course, why did I put this exponent here? So I can use my little reciprocity. This becomes ti to the qj, bj. But now you see, every factor, it's got the same thing, just ti. So I just add the exponents. But of course, what's that sum? By my choice of the bj's. And the point is, I've chosen that to be 1. So in fact, what I discovered is I now know what G is. So in fact, I know that each one of these things is just this T raised to, well, let's see, so what's missing? Yeah, so what's missing is, so let's see, so that is Ti. So Ti is this T, but it's raised to the Qi power. And so T naught is T raised to the Q naught. T1 is T raised to the Q1, all the way through to that for T contained in C star. And so what we get, so notice it's simply a slightly different group action. It's a weighted version. Here we had the version of group actions where all the weights were 1. Now we use the group action where all the weights are n. And the point is that my weighted projective space really is Cn plus 1 minus 0 modded out by C star, where I'm now using this C star action. And notice that it all came from the fan. So basically, everything I did was dictated by fan. So the toric geometry told me, if I, when we defined this weighted projective space using this fan, at that point it was a toric writing. Now we see it actually is the thing that you actually construct in the usual way. And again, this is a geometric quotient because these cones that I get here, they're no longer smooth cones, but they're all simplicial. So let's do another one of our favorite toric varieties. Let's construct P1 cross P1. So the idea is I want to get a slightly more interesting bad stuff. So why can bad stuff be more complicated? So I'm going to keep this on the board. And again, this is one that appears multiple times in the chapter because, one time you compute the group, one time you compute the exceptional set, and the final time you do the quotient construction. So let me label these as a U1, U2, U3, U4. So that means my polynomial ring, it'll be x1, x2, x3, x4. So now it's sort of fun to think about the bad stuff. So for example, take this cone. This cone is going to give what monomial? Remember, the recipe is you use the ray generators that aren't in the cone. So it'll give x2, x3. Simply right here, what monomial do I get? Yeah, x1, x3. So if I use right here, I get x1, x4, again using this cone. And then if I, so let's see, so who have I not used? So let's use this cone, I get x2, x4. So there's the bad stuff ideal. And again, from this I can reconstruct the fan, because for example, this tells me I use the cone generated by the complementary rays, and so this guy corresponds to this cone right here, and then so it all fits together really quite beautifully, and then but now let's think about what z of sigma is. Yeah, so this should be b of sigma, and this actually we wrote down last night. Is one of the examples when you look at this. In fact, well, one thing that's relevant is, this is a nice radical ideal. That means its primary decomposition will be an intersection of prime ideals, and you work it out that you get x1, x3 intersect x2, x4. Let's see, so my labeling is, that's okay. Yeah, so let's see, so I apologize that I actually miscopied stuff from my notes. So let's see, so I called that U1, U2, U4, U3, so that's what you need to get the stuff there. And so it turns out what Z is now you see it's basically this variety union that variety, and so it's the first two coordinates can be 0, or the last two coordinates can be 0. So now the bad stuff is a bit more complicated. So it's a because notice that this is sitting inside of C4, and so I'm in 4-dimensional, and rather than like in this case, our bad stuff was just simply a point. Now all of a sudden my bad stuff has dimension 2. And then what's the group? We've got the group staring us in the face. In general, and I won't go through the details, but it's sort of a fun example to work with. Because it's sort of similar, because notice that I basically have, U3 is, because notice U3 is minus U4, U2 is minus U1. And so when I start hitting this with the standard basis of stuff, you basically, so in this case, there's really two equations that define the group, and you end up, when you work it out, you discover so in this case, the group is very nicely just C star squared. And so what is P1 cross P1? What I'm going to do is actually write two ways to write it. And so one is, basically, C4 minus, this slightly complicated gadget, modulo C star squared. But you can also think of it more naively. What's P1? P1 is C2 minus 0 mod C star cross the same thing. And if you very naively take the product, well, there's a C star, there's a C star, there's a C star squared. This C star acts on the first two coordinates by lambda, and this C star acts on the second two coordinates by mu. So we're going from the C star to C star squared makes perfect sense. Of course, C2 cross C2 is that, but then what set do I have? Well, I have to take the Cartesian product of this with this, and when you take the Cartesian product, you get this paired with C2 and that paired with C2, and that's exactly the description there of Z. So in fact, what the quotient construction gives you is what you'd obtain in a very naive way just by taking the product of the quotient constructions of P1. So it's all fitting together pretty nicely. So let's do another example. This is one of the examples I did last night. Let's now do it from our more sophisticated point of view. And this is one where you'll actually work out some of the details in the exercises, some of the groups. So this is example 5.1.15 and 5.0.2. So you get, this is just E1, E2, E1 plus E3, E2 plus E3. So this is U1, U2, U3, U4. And this is, we've seen that, so this nice cone, and we've seen that U sigma is basically the variety of xy minus zw. Now, I did this construction last night, but let's see how it follows by the quotient construction. So in this case, my fan is sigma and its faces. So that's how you turn a cone into a fan. You just take the cone and throw in all the faces. Is a very simple kind of fan. And then, now how do I get this exceptional ideal? Well, I basically can use the maximal cones. That's the obvious maximal cone. But remember, this means use all of the rays not in sigma. Well, how many rays are there not in sigma? Because these are all the rays I have, and they generate sigma. So in fact, this is, sigma hat, there are none. So in fact, in this case, what is this monomial? The answer is it's just 1. Sort of the empty product is 1. And so what does that tell me about my exceptional set? So where does this vanish? The answer is it doesn't. And so in this case, we don't have to, there's basically no bad stuff to remove. And then when I look at T1, T2, T3, T4, contained in G. Remember that I basically get one equation for each basis vector. And remember that this is a cone in R3. So it's just an E1, an E2, and an E3. And when you work out, here are the ray generators. And when you work out stuff, what you get is basically you get that T1, T4, because you see these, see, did I do that? Yes, to be consistent with stuff, I have to relabel this. My apologies. That's U3, that's U4, that's U2. That's consistent with some of the labelings we've done in the pictures in the book. And so the point is, see, U1 and U4, they're the only ones that involve E1, and that's picking that out. So that's got to equal 1. E2, only this one and this one. And so that's going to be T2, T3. And then for E3, the only ones that involve this one are here. And that gives you, that's going to give you T2 and T4. So when you sort that out, what equations does that give you? That tells you that G is, well, notice that there's going to be some inverses of things. And in fact, what happens is that once I pick the first one for, so suppose I call the first one that one, well, then see that one is going to be a T1 inverse. And then, so in fact, notice that these two equations right here, the fact that those are equal, I can cancel the T4 and I get the T1 equals T2, so that's a T. And then when you look at this one, you're going to get another T inverse. And that's exactly the group I wrote down last night. And then we get that, and so what we get is that in this case, the toric variety of this fan is just the affine toric variety of the cone. And so this is C4. There's nothing we need to remove, modulo. And notice that this is isomorphic to C star. So it's that. And this is example C from last night. And one thing I now know immediately is this a geometric quotient? Because remember the theorem. The theorem says it's always an almost geometric quotient. When is it a geometric quotient? So what does the fan have to be? Simplicial. Is this a simplicial cone? Because I'm in 3 dimensions, I have 4 minimal generators, and so this is not a geometric quotient because sigma is not simplicial. So this is a good place to stop, so we will reconvene at 11.